Now, what is Euler's method to solve a differential equation? So Euler's method is well, a method to construct a solution approximately, and it is based on the following formula, familiar from secondary school, I guess, that y of t plus delta t, if delta t is small, approximately equal to y of t plus dy dt times delta t, right? So if delta t is small. Now, what does it have to do with differential equations? And so suppose that we have a differential equation, dy dt equals f of ty. Then, using this as dy dt in the previous formula, we are going to get y of t plus delta t is going to be approximately equal to y of t plus dy dt, and dy dt is our f of ty times delta t. Well, so now suppose that we want to approximately compute the value of our solution at consecutive points. So suppose that we have our point t0, and we know that y of t0 is y0. And then we have, say, t1, which is t0 plus delta t. And then we want to compute y1, which is going to be y of t0 plus delta t. So according to this formula, is going to be y0 plus f of t0 y0 times delta t. Then suppose we want to compute it at the next point, t2, which is t1 plus delta t, or t0 plus 2 delta t. And we want to compute y2, which is going to be y of t2. Then again, applying the previous formula, this is y of t1 plus delta t. Y of t1 is y1 plus f of t1 y1 delta t. Then if t3 is again t2 plus delta t, then if y3 is y of t3, then according to the formula, well, strictly speaking, these are all approximate equalities, so this is only approximately. This is going to be y2 plus f of t2 y2 times delta t, well, and so on, right? So it means that if we have tn, which is t0 plus n delta t, and yn, which is y of tn, then this is approximately equal to yn minus 1 plus f of tn minus 1 yn minus 1 times delta t, and so on, right? So by doing this, we can compute approximate values of our function at different points. So let me show it graphically. The graphical representation depends on the value of delta t. Right? So suppose that here I write that delta t is 1. So if delta t is 1, and suppose that well, I'm looking at the solution of the initial value problem, y of negative 2 equals 2. So this is my initial point. Now, geometrically, it means that in order to construct the next point, I need to start at the initial point and then follow just this vector until I change t by delta t. So in this case, delta t is 1. All right. So then that's my next point. So this is going to be the point t. If this is t0 y0, then this is the point t1 y1. Then I go in the direction of this vector. This is going to be my t2 y2. Then I go in the direction of this vector, then in the direction of this vector, and so on. This is if delta t is 1. Well, look what's going to happen if say I choose a different value of delta. So suppose it now is 0.5. 0.5 means that I still need to go in this direction, but until here. Then I'm going to follow this direction, then this direction, then this direction, then this direction, then this direction, and this direction. So this is if delta t is 0.5. Well, if delta t is, say, I don't know, let me just give you the next one, no, 0.25. So 0.25 means that, let me choose another color and maybe make it thicker to distinguish. So then I'm still going to go into the same direction at first, but then I'm going to take the step of 0.25, which is a smaller step, and so on, right? So then by choosing a value of delta t, I am going to construct a solution in the form of a piecewise linear function. So it is going to be an approximate solution. It's going to give us give me values at specific points, right? So if, say, delta t is 0.25 and the initial value of t is -2, it means that I am going to approximately compute y of -2, then y of -1.75. It's this. This is y of -1.5. This is y of -1.25, and so on, right? So there is a discrete set of points in t that I'm going to approximately compute my solutions at. But the smaller delta t is the obviously kind of the finer step is, and the better approximation to the solution is. Now this is called Euler's method, and it is actually the simplest method of solving differential equations numerically. And if you want to understand it further, I suggest that you, well, a little homework for you is to program this Euler's method in Matlab. Program in Matlab. So in other words, you need to take this equation and then translate it into a program in Matlab, and then you plot the solution, and then you will see that if you take finer steps, then you get better approximations to the actual solution. Right. So if you're interested in this, please write a Matlab code, and you can say, I don't know, save it into Octave online, and you can share it your program with us through comments to this